Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. So, we are discussing about leaching and extraction, and we have already discussed in our previous few classes on the basics of leaching and extraction, and we have discussed the equilibrium condition in leaching and how we can draw the equilibrium diagram, and also we have seen the extraction process, the basics of extraction process, then equilibrium diagram in extraction, etc. And today we will cover a few more topic in leaching and extraction. So, let us see. So, extraction, basically when we call extraction, we may define two cases, either the solid liquid extraction, that is leaching, and the equipments specific to leaching we have already discussed in our first two classes. Today the equipments that we will discuss, those are used for liquid extraction, or basically the solvent extraction. Okay. And before going into that, I once again try to just recapitulate that what happened in case of these extraction phenomena. So, we have to if any one of you need to design or need to assess any process which involves extraction or leaching operation. So, you have to first move with this, first you have to have the diagram of what is the solvent coming in and what is the other solvent, because in case of this liquid extraction, you have both the stream solvent, both the streams are liquid. Okay. So, here also you may mention that this is solvent and this is carrier. Okay. So, then you have the extract and raffinate, those two stream, and you have to find first that equilibrium diagram that you can read from those equilateral triangle diagram, and if those two solvents are partially miscible, you can have this. So, this will be your component C or A, whatever. Okay. And from that you need to find the fraction of all, then you have to see the material balance. Okay. Then you have to see the component balance. Okay. And always remember, whether it is in the leaching operation or extraction operation, ideal case is that you will get one plot where your operation where your x a by y a, if you plot where your x a is defining the concentration of the solute in the overflow or in the extract, and y a defining your concentration in the raffinate or in the underflow. So, you will have a 45-degree line if the process is exactly or ideal equilibrium condition, but generally it is not that. So, what the condition we will get in each operating step, so that is called the operating line. So, whatever the mass whatever the component balance we will get, from that we can define that if the process is actually deviating, let us say actually deviating from the ideal case. So, you can find in each stage, if you have a multi-stage, if it is a single stage, so you just get one such deviation block, and if it is a multi-stage problem, so you will get a multi-stage or different stages, what will be the fraction and how much from the initial fraction to the final fraction you can separate by this method. Similarly, for the leaching, if you remember, we had this kind of a plot, like if these are the ideal plot for the x a versus y a, and then we have some operating plot which have some variation from the ideal situation. So, all those things are there, and finally, we will come to the equipment section. So, extraction equipments, there are many kind of equipments, and some of the thing we will discuss here only, just to give you a brief idea of their types. So, in the extraction equipment, we have vessel in which the mixing is done by mechanical agitation. We have seen initially that for extraction, the agitation, that mechanical agitation and temperature, these are having an positive role, because this increases the mass transfer, rate of mass transfer. So, for that we need to have vessels in which the mixing is done, and some agitation we need to provide there. Okay. So, agitation may be of different mechanical arrangement we need to provide, but some agitation is required, because it will help in the proper extraction. So, we have agitated columns, okay, mixer settler we are having, and centrifugal extractor, this is also we are having. So, in both the cases we use some motion or some agitation mechanically, or then we can design those vessel for extraction. And mechanical agitation, these three, whereas we can also have this mixing done by flow of the fluid. So, these are spray extraction tower and packed extraction tower. So, extraction should be done where proper mixing of the two phases are there, and the two phases come in proper mixing or in a properly dispersed condition if we provide some mechanical agitation to that. Apart from mechanical agitation, we can also give the flow of the fluid, that is in the form of spray or the packed extraction tower. So, agitated columns, two most important types of agitated columns that is used for liquid extraction. One is the Scheibel tower. The agitators are mounted at fixed interval on a central vertical shaft. So, this is kind of a mechanical agitation that we provide here, and how we provide this? We give agitators at fixed interval. We give agitators, we mount agitators at the fixed interval on a central vertical shaft. Okay. So, there will be one central vertical shaft, and in that we will fix some agitator, okay, that will rotate, and this thing will be kept in the tower. So, wire mesh picking are installed to improve the coalescence and separation of the phases. Okay. So, wire mesh pickings are installed to improve the coalescence and separation of the phases, that is important. And another is the Carr reciprocating plate tower. So, what is that? Here the perforated trays moves up and down. So, the tray itself are perforated, so that the proper mixing will takes place, and they move up and down. So, some shaker kind of arrangement or the vertical shaking arrangements are given to this reciprocating plate towers. So, more uniform drop size distribution we can find here. So, more uniform drop size distribution indicates that proper mixing will be there, and the extraction efficiency will be very high. So, these are the two diagram that showing the Scheibel tower and Carr column. So, in the Scheibel tower you can see that there is a variable speed drive. So, this variable speed drive is responsible for rotating the central vertical shaft at the required speed, and there are agitators mounted at a fixed interval, you can see, and we can provide different kinds of baffles there to have the proper mixing. So, in this the heavy phase is coming in from the top, and that heavy phase will come down eventually. While coming down, that will have the effect of this agitators, there will be some proper mixing, and the light phase is entering into the system from the bottom. So, the heavy phase will eventually come down and exit from the bottom, and the light phase will eventually going to the upper right section and exit, the light phase exit from the upper right section. There are two interface control is given, and if you see that there is the turbine blades are there, these are the turbine blades in one section. If you magnify one section in the Siebel tower and see, so there are horizontal outer baffles and there are horizontal inner baffles. Okay. So, two outer baffles are there and two inner baffles are there. Inside the inner baffles, the turbine impellers are there, okay, and outside there is a vessel wall and there is a rotating shaft. So, this is how this kind of tower operates and help in proper mixing. The car column is that here also the drive assembly is given. This drive assembly operates this in a reciprocating motion, okay. Up and down reciprocating motions are there, these are the perforated trays. So, again the heavy phase is entered in from the top. So, the simple thing is heavy phase always comes from the top, because otherwise we need to use a pump to just throw it from the bottom to the up. So, this design is very common in most of the cases, and then this heavy phase will come down eventually mix with the light phase that is entered from the bottom, and there is a sparger given, and these are the perforated plates, these are the baffle plate, and tie rods and spacers are also given, and then this liquid phase will go out. So, because of this perforation and the reciprocating motion, very well mixing we can observe in car column. So, this is very effective, and there are some other kind of extraction towers also available. Mixer settlers. A mixer settler device ordinarily consisted of two parts. One is a mixture for contacting the two liquid phases and a settler for their mechanical separation. It provides efficient mass transfer. So, what we can see here is that the solvent and the feed enters into a mixing chamber. Okay. So, proper mixing will take place and then it is settled in another chamber which is called the settling chamber. So, in the settling chamber, raffinate which is supposed to be the heavier one will come down and the extract, the lighter one, will float. Now, there are certain system where the mixer and settler are separate chambers are there. In one chamber there will be mixer and then it is moved on to a cylindrical kind of chamber which is used for the settling. But in this mixer settler it is combined system, both the operation mixing and settling or separation is taking place. Okay, so, mixer for contacting the two liquid phase and settler for their mechanical separation, it provide efficient mass transfer. There are other spray extraction towers. The heavy liquid enters at the top and in the spray tower and fills the tower as the continuous phase. The light liquid enters through a nozzle distributor at the bottom and which disperses or spray the droplet upward. So, because of this drop form, they have very high efficiency to mix with the heavy liquid that is coming, and the light liquid coalesces at the top and flows out. Okay. So, all the spray that is the rising droplet form, it is coming and it coalesces and then it going out from the top section, and the heavy liquid that is coming from the bottom and extracted. So, while this light liquid is coming in contact with the heavy liquid and coming towards the top, the solute component or flavor component that is it intend to take from the heavy liquid to the light liquid, that transfer is taking place. So, this is how the spray extraction towers work. So, parameters of liquid extraction. So, first is the solvent selection. Solvent selection, as we have seen that these are very important, because in liquid extraction the two liquid phase are there, two liquid phase we observe here. So, one is having the solvent, generally the pure solvent, and the other is having the some solute plus carrier. Okay. So, since this solute has to come from this phase to this one, and this only come if the chemical potential is higher here, or if it is have the affinity towards this solvent. Okay. So, we have to carefully select this solvent, so that the solute can come out from this phase. So, solvent selection is very important, whether we want to separate some organic material, some flavor compound. So, based on that we can select the solvent, okay, or if it is water soluble simply, so we can use that. Then second is the operating condition. So, operating condition, also in that we can consider temperature as one, because it helps in extraction. When it make the sample in a low viscous sample, so it helps in extraction and mobility is increased. And mode of operation, so there will be mode of operation in the sense the batch operation or continuous operation, then the co-current or counter current operation. So, those will affect the efficiency of the liquid extraction process. Then extractor type, that we have seen many kind of extractor are there, spray type extractor, or it is a like we have seen the mechanical agitator type is there. And what is the design criteria? Okay. So, design criteria, that the full design starting from all the ports, all the inlet and the flow line and the mechanical agitation part. So, all those things are important. Okay. So, these are about the parameters of liquid extraction system. Now, we will move on to one more extraction method that is becoming very common nowadays, especially in some industry. People are going to use that one in a huge scale, because they have some advantage, although the cost may be a little high, but they have some advantage. So, let us see one such very important extraction technique. So, this technique is called supercritical fluid extraction, and with that some other special extraction technique will also see. For example, the separation of protein to aqueous phase when 80 to 90% water is there, like polyethylene and glycol. Then dextran or phosphate salts are there, and so these are the sensitive biological products, and recovery of this we use only the aqueous phase. Okay. So, these are some special extraction methods. So, as I mentioned that we mentioned that supercritical fluid extraction, which is very important technique nowadays. Now, here what happens is that extraction with a solvent held at a pressure and temperature above the critical point of the solvent, and the critical temperature Tc is the temperature above which a gas cannot be liquefied at any pressure. So, look into the phase diagram. What happens is that the pressure and temperature, if we try to increase, so eventually from the solid phase, liquid phase and gaseous phase, after that one condition will come, that is beyond the critical point. Critical point means the corresponding critical temperature and critical pressure when we exceed, then the fluid, then some gases are there that will become in a supercritical fluid condition. For example, carbon dioxide is one such gas that achieve its supercritical fluid condition very easily, and it is having very low critical temperature around I think 31.8 degree Celsius, this much is the critical temperature, and the critical pressure I think it's higher than 10.5 megapascal. So, it is higher than that. So, if we have that much, so then we can have the supercritical conditions. So, what is this condition actually? This condition the supercritical fluid achieves some property which are specific to this condition, and that is neither belong to the gaseous phase nor belong to the total liquid phase. But in this situation, in the supercritical condition, the few parameters of the fluid is increased so much that they enhance in extraction. For example, the solubility of a component, because we know that the gases are of low density at low pressure, right. So, the density of the gas is increased when we increase the pressure. However, the liquids are not changing their density over the pressure. So, almost in a moderate pressure range or in the atmospheric range, those are independent of pressure. So, when the gas are exposed to higher pressure and beyond a certain limit, when its pressure increases and its density becomes higher. So, density reaches almost towards the density of a liquid material. Okay. Although it will not become liquid, but its density will approach to that of the liquid, and that in a way increase the ability to solubilize the component. So, solubility of that fluid is increased. Okay. So, that is why it is helping in extraction, and the effect of pressure is very much observed in this particular case. However, the effect of temperature in the supercritical extraction is not that much pronounced, because supercritical fluid extraction has been developed on this principle, basically focusing on this principle that above the critical point, if we change the pressure, if we increase the pressure, then the solubility of the component in that supercritical fluid will increase. But if we look for temperature change, so around 10 megapascal pressure, temperature will not positively affect the extraction rate, rather it will degrade that. And even if the temperature increases when the pressure is very high, around 30 megapascal or so, then again the temperature will cause the positive effect, but the intermediate phase it will not have that much effect, or till not known that much, that what is the mechanism exactly for the for that the temperature will help, right. So, supercritical fluid as solvent. So, because of this property that at the higher pressure this supercritical fluid will behave in such kind of a liquid which has higher solubility, and therefore, it is acts as a solvent. So, the power of a supercritical fluid, or actually a compressed gas, to dissolve a certain substance is approximately represented by a value called the solubility parameter. Okay. So, this is the solubility parameter, delta. So, solubility parameter is expressed by this equation 1.25 Pc, that is the critical pressure, to the power 0.5 into rho g by rho L. So, density of gas and density of liquid, these two ratio. Now, we can see that when the gas is compressed, so the solubility is very highly increased, okay, and this is the benefit that we try to take out. So, this is why, because of this solubility increase of this supercritical fluid under high pressure, we try to use this as a potential solvent for solvent extraction method. And temperature, as I have already mentioned, that effect of temperature is not that much pronounced. However, sometime what we do, that as a co-solvent we add some other solvent to this supercritical fluid, and that in a way increase the dissolution capacity of this supercritical fluid. So, normally carbon dioxide is very common supercritical fluid, and in many food processing sections now they have started using this supercritical extraction technique. So, this is useful for useful solvent for supercritical extraction is generally carbon dioxide, as I mentioned, this is very common, and its temperature is 304.1 Kelvin. Okay. So, as I mentioned that 273 is 273 is our starting point. So, from that we can consider that it is, if it is 0, then what will be the temperature in Celsius, and P c is generally 7.4 megapascal. So, in supercritical region no distinction between the liquid and gas can be done, as I mentioned that those they will gas, but their density will approach to the liquid. No phase transition will be observed, and the supercritical fluid acts like a very dense gas or light mobile liquid. Solubility and selectivity. So, as I mentioned that the solubility and selectivity, this is a strong function of temperature and pressure. So, not only supercritical gas will increase the selectivity, they can be used for many number of solute or many number of components. So, because of their broad selectivity, that is one advantage. Second advantage is higher solubility, and we have seen that it is a strong function of pressure and temperature when the pressure is at some higher range. Okay. So, total extraction of the solute is possible when the pressure is highest, and selective removal of odor producing volatile components close to the critical point. So, close to the critical point we can separate the odor producing volatile components also. So, in this particular case the solubility may be smaller, but the selectivity is much higher. Now, we will have a quick look on how the operation of supercritical fluid extraction takes place. So, there are some part that we need for supercritical fluid extraction. So, let us see this is the phase diagram of supercritical carbon dioxide. So, we have in this zone initially where the extraction takes place. So, extraction takes place in the supercritical region, that is beyond the gas and liquid region, when you have the critical temperature you have exceeded and the critical pressure that also you have exceeded. Okay. So, you have exceeded the critical pressure and temperature. So, we then have a extraction vessel. We then have a extraction vessel where the extraction actually happens. After extraction we need to separate that, because extraction means we have the supercritical fluid and we have the solute or the component that we have extracted, okay, from the other solvent. So, then or from the feed solution. So, then we need to decrease the pressure. When we decrease the pressure, then no longer the solubility is higher. Okay. So, all the component will be separated, and the this carbon dioxide in a gas form we will get. Now, then we will get the carbon dioxide in a gas form, we will separate that, in a separator, and after separation the product will come out from the bottom, because that will be deposited and the gas will taken out to a cooler. So, what we do now, further the temperature is lowered in that cooler. Okay. The temperature is lowered, and when the temperature is lowered, the gas is become eventually the liquid. So, there is a heat exchanger here that helps in that liquefaction of that carbon dioxide, and after that, that will be taken in a tank. All the liquid carbon dioxide is taken in a tank, and again since we need to increase it from the lower pressure to the higher pressure side. So, we increase the pressure by compressor. Okay. that compressor increase the pressure of that liquid carbon dioxide, further we increase its temperature by again passing through a heat exchanger, and then it is entered to the extraction vessel, and the same process will be repeated. Okay. So, supercritical region is there, then there is a lower pressure region, then lower temperature, then again increased pressure and increased temperature, and basically we can categorize this to a higher pressure side and the lower pressure side. So, in the higher pressure side the compressor, the heat exchanger or heater and the extraction part is there. In the lower pressure side we have this expansion valve, we have separator and this heat exchanger for cooling of the supercritical fluid. Okay. So, here we can see that the solvent recycling, when we are doing, we are using the pump, and then by using that we are sending it to the high pressure section, then the CO2 and the solute is the pressure reduction will be there. So, that means we can see that without applying any extra energy, we can just by lowering the pressure we can separate the solute and the supercritical fluid. So, like in other extraction we have seen that we need to apply the distillation or crystallization to separate the solute and the solvent, but here the extracted material is very well can be separated by just pressure reduction. Okay. So, this is very efficient method in that way. Now, commercial process is decaffeination of coffee, this is done by supercritical fluid extraction. So, commercial process is decaffeination of coffee from the caffeine, which is having 0.7 to 3% caffeine, that we can extract up to 0.02% by using the supercritical fluid extraction. So, this is how this method is very beneficial. So, this has some advantage and disadvantage, we will quickly look into them. First, let us see the advantages of supercritical fluid extraction using carbon dioxide. So, here we can operate it at moderate temperature of operation. We have seen that the temperature is around 304 Kelvin or 31.8 around degree Celsius. So, it is very helpful to operate, there is no high temperature needed. So, the heat sensitive material will also can be very well preserved. Carbon dioxide is considered to be non-toxic, non-flammable and nature friendly. So, using this liquid supercritical carbon dioxide does not have any ill effect on the product or that, and it does not have any residue also on the product. It is very volatile solvent. So, when we try to separate this at the low pressure, it completely gets separated from the solute or from the component that we want to separate, no residue is found on the product, and good mass transfer due to low viscosity. Okay. So, although it have in a supercritical state, its density is increases towards liquid, but its viscosity remains low. So, because of this property, low viscosity and high density, the solubility increases. Okay. So, that is helping in a mass transfer. And selective dissolution, this is another, that the selective dissolution happens in case of liquid carbon dioxide for most of the material. So, that way it is very advantageous. Now, what are the maybe the negative points of supercritical fluid extraction? So, limited solvation power, and this can be overcome by adding some co-solvent, as I was mentioning that sometime what happened that with this supercritical CO2 some other solvent is added, and that in a way helping that will mix properly with that, and they will increase the solvation power of this supercritical fluid. And higher operation pressure. So, pressure is definitely one thing that we need to design proper system for that, and for that the mechanical arrangements, the equipment thing will increase, and the cost will also increase, because initially you have to have a very huge setup for all this pressure increase thing. So, the initial cost will be very high, and there is a difficult to run as a continuous process. So, there is a difficulty to run this as a continuous process, and although we need to look for more advancement in that, but still in a batch process also this is an efficient one if initial cost is more, but if we can run it on the continuous basis and for a long run we can get very good advantage of supercritical fluid extraction, because eventually the running energy that requires in case of separation, because maybe we have not mentioned that, but ideal case is when we go for extraction or leaching process, the energy needed in the extraction is very less, but energy needed in separating the solute from the solvent or the solvent from the product of the solid slurry, that takes a huge energy, because there we need to apply the evaporation or distillation or those kind of technique which are very energy intensive technique. So, there actually 85% of the energy of the whole process is getting wasted, or not waste, we can think of utilizing there itself for separation, but for extraction we generally use 15 to 20%. So, if we use the supercritical fluid extraction, maybe that separation thing is no cost involvement required, because it can very easily by lowering the pressure we can separate. So, maybe that extra cost that we can reduce there can be utilized for the initial setup preparation. So, that way it is very beneficial. So, this is all about the thing that will cover in extraction and leaching, and we have come to the end of this particular topic. And if you have some specific discussion, because we have not gone too very deep about this leaching and extraction process, but and there are a detailed mass transfer analysis is also required. I hope you will refer to that mass transfer in other courses that are running on the mass transfer. Many courses are there, and if still you have any specific query, please send that to us. So, I will try to clarify them. Thank you.